Today I read this article or exploration paper as a former-based approach for efficient RISC V processor verification. The openness of the RISC V allows customizing and extending the architecture and microarchitecture of RISC V based core to meet specific requirements. This appetite for more design freedom is also shifting the verification responsibility to a growing community of developers. Processor verification, however, is never easy. The very, the very novelty and flexibility of a new specification result in a new functionality that inadvertently creates specification and design bugs. During the development of an average complex RISC-V process core, you can discover hundreds of or even hundred thousands of bugs. As you introduce more advanced features, you introduce new bugs that vary in complexity. There are certain types of bugs that are too complex for simulation to find them. You must augment your RTL verification method by adding a formal verification. From corner cases to hidden bugs, formal verification allows you to exhaustively explore all states within a reasonable amount of the processing time. In this article, we go through a formal-based, easy-to-deploy RISC-V processor verification application. We show how, together with the RISC-V ISA code model and the RISC-V compliance, automatically generated checks, as we can efficiently target bugs that would be out of reach for simulation. By bringing a high degree of automation through a dedicated set of assertion template for each instruction. This approach removed the need for devising assertion manually, thus improving the productivity of your formal verification team. 1. The context. CodaShip L31 is a 32-bit mid-range RISC-V embedded core for microcontroller applications. As a versatile, low-power, general-purpose CPU, it balances performance and power consumption. From IoT devices to industrial and automotive control, or as a deeply embedded core and a larger system. It brings the local processing capability into a compact area. Designed in Coda AL language with the CodaShip Studio, this fully customizable core includes classic extension and features and needed efficient and thorough verification. It is L1, L31, and the L31F is optional. The interrupt controller, WFI, RISC-V debug, and the CPU RV32IMC and RV32IMCF. Branch predictor, physical memory protection, instruction cache, ITCM, data cache, DCTM, and a multiplier divider and a VU, user customer extension. That is, Figure 1 CodaShip L31 block diagram. Table 1 is CodaShip L31 features. The instructions architecture ISA is RV31IMCFV. Pipeline, 3 stages in order. Branch predictor, optional, increase the single thread performance. Multiplier, parallel implementation, single cycle multiplication. Divider, sequential implementation. Memory protection, optional, MPU with 2, 4, 8, 16 regions. Physical memory attribute with a 2, 4, 6, 16 regions. Machine and user privilege modes. Tightly coupled memory TCM. Instruction and data TCMs. Customizable size up to 2 megabytes. AHV write to TCM secondary port. Interfaces. 32-bit AHV write interfaces for fetch and data. AXI write with caches. Floating point unit, FPU, optional single precision. Debug, standard RISC V debug, 2 and 4 JTAG pins, 2 to 8 breakpoints and watch points. System bus access. Interrupt. Interrupt controller. Standard RISC V clean tail implementation. Up to 128 interrupt. WFI and NMI. Our verification approach. Processor verification requires strategy, vigilance, and completeness. Verifying a processor means taking uncertainty into account. What software will run on the end product? What will be the use cases? What asynchronous event could occur? These unknowns mean significantly opening the verification scope. However, it is impossible to cover the entire processor state space, and is not something to aim for. The process quality must be ensured while making the best use of time and resources. Doing smart processor verification means finding relevant bugs efficiently and as early as possible in the product development. At a high level, our verification approach is based on the following. Verification is done during processor development in collaboration with the design teams. Verification is a combination of all industry standard techniques. Using multiple techniques allows you to maximize the potential of each of them and efficiently cover as many corner cases as possible. Verification is an ongoing science. What works as a combination of techniques that evolves as processors become more complex. When verifying our L1 L31 core, the idea was to make simulation and formal verification complement each other. 2.1 The benefit of and a purpose of simulation. Simulation is de facto must have. It's allowed us to verify a design at two levels. Top level, mostly to ensure that the design conforms to its specification, the ISA for a CPU, and the most common situations. Block level, to ensure that the microarchitecture is designed as it was intended to be. However, it is difficult to link these checks with a high-level architecture specification, as this usually relies on the directed random test generation. Hence, the being able to reach tricky and uncommon situations. The top-level simulation unusually does not stress the design as much as a block-level simulation does. Therefore, overall verification of the design against the ISA is achieved, but with a low level of stress. 2.2 Benefits and purpose of formal verification. Formal verification uses mathematical techniques to provide definitive answers about the design to questions written as assertions. Formal verification tools perform an exhaustive analysis of the combination of the assertions and the design. There is no need to specify any stimuli except to specify some illegal cases to avoid false failures. Tools can provide a proven answer, which is exhaustive, or a failed answer, also producing a waveform showing a stimulus proving the assertion to be false. On large and a complex design, tools sometimes only prove a bounded proof, meaning that no fair scenario exists from the set up to a specific number of cycles. Different techniques exist to either increase the cycle number, or get a proven or a failed answer. The formal verification is used in the following cases: to fully verify a block, potentially removing the need for a simulation. Due to the computational complexity of a formal only sign-off is limited to a small modules. To verify a block or even a large one, in addition to a simulation, because former is able to find bugs in corner cases and random simulation can reach only by luck with a low probability. To handle some verification tasks where simulation is not adequate, for example, clock gating, X propagation, CDC, equivalence checking, and etc. To help investigate known bugs for which debugging information is lacking, and to qualify potential design fixes. To classify and identify bugs so as to learn and improve the test benches and simulation thanks to finding informer. To potentially help simulation, filing, fill, filling holes in coverage. 3. The solution. Former-based approach for efficient RISC-V processor verification. We decided to use the Siemens EDA processor verification app. Siemens EDA processor verification app to efficiently verify our L31 RISC-V core. The purpose of this tool is ensure that a processor designed at a RTL level correctly and exhaustively implemented the ISA instruction set architecture ISA specification. 3.1 An end-to-end approach. From a high level and repeated golden model, the tool generates a single cycle execution model of the ISA envelope, a set of assertions which checks the design under test, duty, and model are functionality equivalence at architecture level. Note, this is not doing any formal equivalence checking. When new instruction I is fetched into duty, the architectural state duty init is captured. The instruction is executed in the pipeline. Another architectural state duty final is captured. And is fed with duty init and I and computes a new M final state. Assertions check assertions check that the response in M final is the duty final have the same value. Figure 2. End-to-end verification flow for three-stage and L31 core when a verified instruction I is neither stored or nor flushed. This end-to-end verification approach is achievable with a reasonable effort on blocks, which is possible to write an end-to-end assertion on a cache to verify that the data written at a specific address is correctly read from that same address. This uses well-known formal verification techniques such as a scoreboard. Therefore, a CPU, however, writing such an assertion is not doable manually. It would be not a, it would need to specify the semantic of each instruction, cross with or execution mode. This is usually not done at all. The formal verification of a CPU is split into smaller pieces. However, verifying that all pieces together correctly implement the ISA is still missing. Using the proposed approach means that we were able to verify the full L1 core at once without having to write any complex assertions. As described above, the golden model and the checking assertions are automatically generated. This approach is at the same time highly configurable and automatic, especially for RISC-V CPU such as L31. The user just specify a high-level RISC-V parameters and extension that the design implements. The tool is able to automatically extract data from the design, such as linking architectural registers with the actual flip-flops. The tool allows adding customization, such as a new instruction to verify, with the ability for the user to extend their gold model. Finally, the fact that a golden model is not developed by the Kodashi, except for a customized part, provide extra guarantee, which is important from a verification independent point of view. 3.2 Section 3.2 How we used the Siemens ED processor verification app. Before we could use the tool, we needed a formal verification setup for the RISC-31, RISC-V core. This setup is similar to one used for formally verifying standard assertions using a assertion-based verification (ABB) approach with abstraction, constraint, and etc. The tool allows you to verify specific classes of instruction and do disable some resource checks. With that, we could start the verification with a reduced space consisting of only the simplest instruction. For example, only the integer, arithmetic, and logic instructions. Only the simplest but most important checks. For example, the update of general purpose registers. Other checks that can be added later on are the update of the system registers (CSR) or a programmable program counter PC and memory accesses. And the main functional mode to no interrupt, abort, exception, or debug accesses. The three orthogonal constraints can be relaxed on one and by one, depending on a critically of the microarchitecture features. The classic formal verification techniques can be used to help get results on the checker assertions, abstraction, design reduction, and case splitting, invariant generation, semi-formal bug hunting, and etc. The result 3.3, the result. This form-based approach allowed us to find corner cases, gave us the insight to improve our simulation and test benches. This verification work was completed toward the end of the project. After our simulation-based verification flows was learning, we started finding a new bugs, which allows us to find genuine and non-trivial bugs. Let's focus on the three items. Found the Siemens ED processor verification app on L31. The 3.3.1 a branch predictor corruption. With this bug, returning a PC address that previously held a jump or branch instruction causes branch predictor to falsely predict the jump to another address. This corner case is found when following conditions are met. Self-modifying code start store current PC plus 1 location of next to JALR JALR2 label 1. This will later become a knob. Exit Level 1 update memory contents and JALR location, for example, to become a knob. Branch it back to start. An extremely rare version of this bug also occurs when an undefined instruction is added. Exception on a new instruction. Where is the where is that? Store current Peter generator level 1 general location. For example, undefined instruction. What? No, okay. This will be later become an undefined instruction. This was found by an assertion checking PC value. The immediate consequence of this bug is a branching, that is, a wrong taken, causing the wrong execution of the code. The bug was fixed by correctly flushing both the branch prediction and the pipeline. Finding this bug with the Siemens ED processor verification app took 8 cycles and 15 minutes of the runtime. Reproducing it in a simulation requires a random generator to support a self-modifying code that returns exactly to the same address that modified the address from a branch to another type of instruction. In other words, it's highly improbable that a random generator could do that. Only a discrete sequence could. knowing the details of the bug. 3.4 Multiple execution of the same instruction. With the bug, MPC, next PC, unit store is raised, which causes the same address to fetch it multiple times. Each instruction executes and retires. This corner case is found when a following condition are met. The core is configured with the TCM. Specific delays are seen in the fetch bus, and specific stores are seen inside the pipeline. The immediate consequence of this bug is still that it is not handled properly in the rest of the pipeline, causing multiple execution of the same instruction. This bug was fixed by correctly handling store in the rest of the pipeline. Find this bug with the GMSCD processor verification and to 5 cycles and 10 minutes of runtime. Reproducing it in simulation requires random pattern of the random delays and stores, but also quite some luck to reproduce this particular sequence. Next is the 3-5. Legal. Fence I instruction considered illegal. With this bug, fence instruction is handled by CSR unit. If the instruction bit corresponding to the CSR address bit of a CSR operation, bit 31 down to 20, matches certain CSR registers, such as the debug and counters, and then the fence can be falsely marked as illegal. This corner case is found when the following conditions are met. These there are random bits in IMM 31 down to 0, RS1 RD. This bit matches some other illegal instruction. This unused field of the fence that instruction, IMM 31, RS1, and LD, are reserved for the final grain fences in the future extension. The forward compatibility based implementation shall ignore this field, and standard software shall zero this field. The immediate consequence of this bug is an illegal instruction exception that is wrongly raised. This bug was fixed by correctly decoding the full instruction on each part of the pipeline. Finding this bug, the Siemens EDA processor verification app took only 8 cycles and 5 minutes of runtime. Reproducing a simulation is tricky because the compiler will only create the simplest implementation of the binary encoding. It requires either a special compiler to create a variation of illegal encodings or a special directed test with various encoding. The benefits and conclusion. Applying this methodology provided a productivity gain for verification teams. Efficiency increased by at a key phases of the project, although the building a correct setup requires effort at the start. Progress accelerated as added new instruction classes and new checkers. This sweet spot was where was where we found the majority of these issues, with the rate of slowing down as we reflect the constraint to allow to explore more esoteric modes of the operation. The figure 3 sweet spot for best efficiency in verifying utilities as core. Mm. Standard function mode, or function mode, simple instruction, or instruction, and main checks and all checks. Overall, the using HMSCED processor verification app was efficient because the overall work required to verify the entire CPU using this tool was much lower than trying to reach a similar validation quality manually. Of a total of 30 bugs and 15 were found in the formal verification. Table 2. Simulation effort and formal verification effort. The verification technique in simulation and formal verification. Verification instruction infrastructure is test bench, random, instruction generated in checker, a solution provided by the Siemens EDA processor application app. Development time, the person year of the output, very limited, only needed to customize the generated setup. Runtime, thousands of testing seed, thousands of thousands of simulation hours. Full proof in 2 hours of runtime, best case. Simulation and formal verification are very powerful when combined to reach higher quality to allows us to feed the virtuous circle of the verification improvement. Figure 4, reaching a best-in-class quality throughout continuous improvement. Find a bug, understanding and learning from it. A verification bug and a design bug. Improve the verification and fix the verification. Fix the design. Yeah. The implementation of this solution for L31, a three-stage microcontroller, proved to be successful and is now deployed to our next generation RISC V cores, both in embedded and application spaces. With the knowledge built by the using Siemens EDA process verification app and 31, the effort to get a robust setup is reduced for application cores, even if they are more complex. Next step include further work to understand how this tool can apply to a superscalar and out of order cores, and supporting new RISC-V extension as they come. CodaShip The CodaShip is a processor solutions a company which helps to differentiate their product. We are Europe leading a RISC-V company with a global presence. Billions of ships already use our technology. In the today's technology market, differentiated everything. The difference between a success and failure. And in the chip design, this difference is quite literally wafer thin. With the increasing transistor codes, your developers can no longer rely on a semiconductor scaling and legacy processors to achieve your goal. The only way to forward it is to implement custom compute with the design tailors to your applications. We deliver a custom compute through the combination of OpenRISC-V ISA, the CODA chip, the studio processor design and automation, and a high-quality processor IP. Our innovative approach lets you easily customize and differentiate your design. You can develop high-performing and game-changing products that are truly transformational. Thank you.